Hey everyone, let's go and finish equilibriums, what I've just typed, so I'm just going to crack on if that's okay. Right, so this is where we got up to. I've still got the notes sort of loaded onto my iPad, so that was the very last thing we did. So it was a calculation, an ICE calculation I call them, for KP. So the first thing we're looking at this afternoon is homogeneous and the difference between homogeneous and heterogeneous equilibria, and then we will have a look at some heterogeneous calculations. And then the final part of the lesson is literally just explaining equilibrium shifts in terms of the equilibrium constant rather than in terms of Le Chatelier's principle. So first year you tend to get asked to explain the shift in equilibrium in terms of Le Chatelier's principle, whereas in second year you could still be asked that, but you might also be asked to explain it in terms of the equilibrium constant. So it's a slightly different way of explaining it. Okay. All right then, so far all the examples that we saw, so last Wednesday basically, were examples of homogeneous equilibria since all species were in the same physical state. A heterogeneous equilibrium contains species that have different physical states. So quite straightforward that. So you can see those 5 equilibria all involved species with different physical states. I won't go through them all because you get the idea. You probably already know the idea. So in the first one, we've got a gaseous species, we've got a solid, and then we've got more gaseous. Okay, and then let's have a look at the last one. You've got solid, and you've got aqueous and solid again. Okay, so fairly straightforward differentiating between homogeneous and heterogeneous. So when you write the Kc expression or the Kp expression for a heterogeneous equilibrium, we must leave out any species which are pure liquids or pure solids. And basically that's because their concentrations are constant, essentially constant. Okay. So again, I'm not going to do all of these because it would take too long into the lesson, but I'm sure you'll get the idea once we do a couple. So these are the same equations in the bullet points there. So obviously these are the notes I give to my students, so this is my way of giving them some practice at writing Kc and Kp expressions again. So if we look at the first one, so remember Kc, we use square brackets, and we need to leave out anything that is a solid or a liquid. So the terms on the top for this one would be the hydrogen. Notice these aren't balanced with any numbers, so there's no powers involved, multiplied by carbon monoxide all over the H2O gas, or the steam in other words. So that's what that would look like. So basically we don't include that carbon solid. If we were doing the Kp expression, I'm going to take a leaf out of your books and see how I feel doing this. So remember on Wednesday I was going on about using round brackets, which is fine. I did have a look in various sources, textbooks, websites, and you do see advice from people saying don't use round brackets because then the temptation could be to write square brackets. So this is a bit alien to me because I've always used brackets. So that would be the partial pressure of hydrogen multiplied by the partial pressure of carbon monoxide, all divided by the partial pressure of that steam, that H2O gas. Okay, so that's the Kp expression. I'm just looking at one, maybe we'll do every other one, shall we? So Kc for this one here now. So what have we got? in the Kc expression, remember we're leaving out solids and liquids, so the only product that we're going to include is this hydrogen. Oops, I've put squared there, it should be to the power 4, shouldn't it? Because it's balanced with a 4. And that's divided by H2O again to the power 4. And then the final one is partial pressure now. And I'm trying my best not to put brackets in. H2 to the 4. Feels weird this, not having brackets, I must say. Partial pressure H2O to the 4. Okay. And then the final one, so we'll do this one. Oops, I don't know where that's gone. So what's going to go into the Kc expression? So we're leaving out the solids. So it's the Cu2 plus concentration all over the Ag1 plus squared, because it's balanced with a 2. And a bit of a sort of trick one, this one. There's actually no Kp expression to write for this one because there's no gaseous species. So just right there, no Kp expression because there are no gaseous species in the equilibrium. Okay, I can't imagine you get asked to say anything like that, but we don't want the table sort of being unfilled. Okay, so that was that. The brackets, so Luke, yeah, Luke's one of mine. Brackets I do. Luke, I agree. I much prefer the brackets in. I must say, it just looks wrong to me. But that's probably because I was taught with brackets back in the 80s. So that's a long time for me to be writing partial pressure expressions with curved brackets in, and now I'm not writing them. It just feels very, very strange. So there, I might just go back to round brackets with my students. Okay, so we'll practice a couple of calculations. So the first one there, when steam was heated with excess carbon to 1200 Kelvin, an equilibrium pressure, and an equilibrium pressure of 15.5 atmospheres, 90% of the steam was converted into hydrogen and carbon monoxide. Calculate Kp for the equilibrium. So the first thing I'm going to do is write the Kp expression. I'll just squeeze that here. So Kp is equal to the partial pressure of hydrogen multiplied by the partial pressure of carbon monoxide all over the partial pressure of the steam. Remember, the carbon's not featuring in that Kp expression because it's a solid. So we're going to do an ice. I call them ice calculations. Remember, some people don't bother with the C, but I quite like to include it. So these are moles. Okay, so we're not told the number of moles, so I think this is where some people might find this a little bit tricky. So all I'm going to do is say, all right, let's assume we've got 1 mole of that. We're not bothered about the carbon, so I'll just put a dash for that. And 0 moles of those two initially, because nothing's happened yet. And we're told that at equilibrium 90% of the steam gets converted. So basically per mole, so I've chosen it to be 1 mole. You can pick any number you want really, as long as you sort of do 90% of that. The easiest thing is to just go with 1. So that's going to drop by 0.9. 90% of 1 is 0.9, which means that at equilibrium you've got 0.1 left. So now we'll factor in the mole ratio. So for every mole of steam, a mole of hydrogen is produced, so that's going to go up by 0.9, that's going to go up by 0.9, it's all 1 to 1. So therefore at equilibrium you've got 0.9 of that and 0.9 of that. So your total moles, should always do this at your equilibrium moles, total moles is 1.9. So what do we do now? We work out mole fractions. mole fractions. How much room have I got? Oh, not very much. Right, I'll have to do them across here. So the mole fraction, remember, is the moles at equilibrium over the total moles. So that would be 0.1 divided by 1.9. So that's 0.05, 0.05263, 0.9 divided by 1.9. So that's 0.4737. And this is obviously the same, isn't it? 0.9 divided by 1.9, 0.4737. And what you can do at that point is, remember, check they all add up to 1. So I'll just put that in brackets, or in red, sorry. Check add to 1. So they will do. So I'm just going to move on. Partial pressures. So remember, that is the mole fraction multiplied by the total pressure. Total pressure is 15.5 atmospheres. So that is 0.05263 times 15.5. Oops, sorry. 15.5. So that's coming out at 0.8158. So that would be ATM. Should really put the units in. This would be 0.4737 times 15.5, and that is 7.342. And I may as well put it in full. This one here, that's ATM, isn't it? 0.4737 times 15.5, 7.342 ATM. And now we're at a point where we can stick those numbers into that blue KP expression. The other thing is obviously check that these add up to, add to 15.5 total pressure, which they will do. And then finally, I'll go to blue so it stands out. So KP is going to be equal to 7.342 times 7.342. You could just say 7.342 squared, but then it might look a bit weird because it doesn't tie in with that. Divided by 0.8158. And we get 67.7 for the number. The units, remember these are all ATMs, so you've got ATM times ATM divided by ATM, so you're left with 1 on the top, so the units are atmospheres, and that's it. So if anybody tried that between Wednesday and Friday, hopefully you're sort of patting yourself on the back because you got it right. So well done if you did. Okay. Right, next one. Quite a tricky one, this one. So carbon monoxide is placed into a closed container with an excess of iron 2 oxide and heated to 1000 degrees C. The equilibrium pressure was 200 kilopascals. Calculate the partial pressures of the carbon monoxide and carbon dioxide. And in red there, your Kp value is 0.403. So first thing you should do is write the Kp expression. So that's the partial pressure of the CO2. Remember, we're only bothered with the gases, divided by the partial pressure of the carbon monoxide. Right, so the way I've done this is I've said that we're going to let, it's quite a tricky one, this one. I'm going to use a bit of algebra to solve this one. I know somebody was asking on Wednesday for a quadratic equation solved Kc expression, which isn't going to be asked, but something like this could be if they're wanting to sort of squeeze out your A star sort of question. So I've said let the partial pressure of the carbon dioxide equal X. So therefore that 0.403, so note the Kp value is going to be equal to X, the partial pressure of carbon dioxide. So the partial pressure of the carbon monoxide is going to be the total pressure minus the partial pressure of carbon dioxide, so 200 minus X. So rearranging that now, so we've got X by itself, 0.403 multiplied by 200 minus X equals X. So the chemistry is over now, it's just maths now. So all I've done there is taken that up to there, multiplied them. So we're getting 80, so that times that, and then that times that. Good old GCSE maths. 80.6 minus 0.403 X equals X. So tidying that up, we get 80.6 equals 1.403 X. Therefore, X equals 57.4 kilopascals. I think the pressure, the pressure is in kilopascals, so these will be kPas. And to get the other partial pressure, remember that X is the partial pressure of CO2. So the partial pressure of carbon monoxide is just 200 minus that, minus 57.4. So that comes out at 142.6 kPa. So yeah, that's a sort of bit more of a nasty type of Kp expression, but sorry, I'll just turn this on to silent. Yeah, so I like to include that in the notes for my students because it's a bit of a different sort of type of question. I'll just make a note of this if you haven't come across. There's a really, really good textbook by a guy called Jim Clark, and it's basically if you want some extra calculations for your A-level chemistry, shell out, well, if you bought it new, I think it's about 21, 22 quid on Amazon, and it's basically 300 and odd pages worth of calculations just for chemistry. So it's absolutely brilliant. So chapter 7 is the equilibrium chapter. So if you wanted to practice any type of calculation for chemistry, I would strongly recommend you shelling out 20 odd quid on that. I think if you went on eBay or something like that, you could get it a lot cheaper. Don't understand why you did 200 minus X. So the partial pressure so we've said the partial pressure of carbon dioxide is X. The total pressure is the sum of the partial pressures. So the partial pressure of the other thing will be the total pressure minus X. Okay. Right, so I think that's all the calculations over. Let me just do a quick scroll through the notes. I think it's all sort of it's all wordy stuff now, which I'm sure you'll be pleased to hear. It's quite a lot of pages, but you'll find that you're just going to be writing the same sort of stuff. So that's good, isn't it? Okay, and actually I think I'll repeat myself on some of this that I've put at the start of the notes. Okay, right, let's crack on. Right, so this is all about controlling the position of the equilibrium, but we're going to move into explaining it in terms of Le Chatelier's principle rather than, sorry, we're going to do it in terms of the equilibrium constant rather than Le Chatelier's principle. So in year 12, remember these are my students' notes, so it's kind of phrased towards them. In year 12, you learn how to apply Le Chatelier's principle to predict how the position of an equilibrium shifts in response to an external change. So this is just a bit of revision. So if in terms of Le Chatelier's principle, if you want a greater yield of product C, how could you achieve that? So the thing we need to look at is what's the sign of the delta H? It's negative, so it's an exothermic reaction. The forward reaction is. You've got all gaseous, so the pressure, remember we look at the number of moles each side, so we've got 4 moles on the left, we've got 2 moles on the right. So what's going to push this equilibrium over to the right? So in terms of pressure, if you increase the pressure, that would favour the side with the fewest moles, which is the right, so that would push it over to the right. What kind of a temperature is going to favour the forward endothermic reaction? It's going to be a low temperature, so lowering temperature. What could you do with concentrations? So if you wanted to push the equilibrium over to the right, you could increase the concentrations of A and B. Increase conc of A and B, so the reactants concentration increased will force the equilibrium over to the right. Or you could lower the concentration of the product and that would force the equilibrium over to the right as well to replace it. So removing C, the product, or lowering the concentration of C, you could say. Okay, so we actually did these diagrams at the start of the topic. So if you remember pictorially, so at equilibrium, if you've got a higher concentration of products to reactants, your Kc value would reflect that by being greater than 1. If it was the other way around, so reactants, a higher concentration than products, Kc would be less than 1. And if they are the same, Kc would equal 1. And then you've got the double greater than. If this box here was absolutely enormous and this was tiny, then Kc would be much greater than 1, wouldn't it? So if I get a green pen, so that would be Kc much greater than 1, which was asked in an A2 paper a couple of years ago. What's the significance of that was the question. It was only worth a mark, but I think it caught a lot of people out, judging by the examiner's report. Okay. So, when the reactants or products of reversible reaction are mixed, equilibrium is achieved when the concentrations, if it's Kc, or the partial pressures, if it's Kp, of the species at equilibrium give the value for K for that temperature. Okay, so I'm going to highlight that because that's key to this. So the equilibrium needs to get the K value for that temperature. Okay, so at a set temperature, the K, the equilibrium constant, is constant. So it has a constant, or it has a set value for a particular temperature, and it's not changed by changes in concentration, pressure, or addition of a catalyst. So if you change the concentration, the pressure, or you throw a catalyst in, Kc or Kp will not change. The only thing that can change the value of K, Kc or Kp, is a change in temperature. It's the only thing. Okay? So the system is in equilibrium when the partial pressures or the equilibrium concentrations get the K value for that temperature. I know when I teach this in class, you're checking students' faces for who looks a little bit confused, because this is quite can be quite confusing. Okay, so we're after the K value for that temperature. That's kind of what I would keep in the back of my head. I want to get the K value for this temperature. If I change the pressure, the concentration, or I put a catalyst in, K won't change. If I change the temperature, K will change. So you'll see all that in action now, okay? Right, so explaining equilibrium shift in terms of the equilibrium constant, Kc or Kp. So let's look at exothermic reactions first of all. So we've got an exothermic reaction. You can see that because of that Kc value, or Kp value, sorry, what am I talking about? The delta H. Trouble is, I'm sort of looking at comments coming up and I'm getting confused with myself. Right, so that there's the exothermic evidence. Okay. Right, so let's have a look. What's happening to the Kp value? It's gone from, at 500 Kelvin, Kp has a value of 2.5 times 10 to the 10. Atmosphere to the -1. We won't bother with the units. When you increase the temperature to 700, Kp goes to 3 times 10 to the 4. So basically what's happening here for this exothermic reaction, Kp has gone down as temperature has increased. So that's something that you need to remember. Okay, so for an exothermic reaction, the equilibrium constant will decrease if you increase the temperature. So as temperature increases, Kp values decrease, showing that the equilibrium position shifts to the left. I'm going to put that in brackets because really the main thing is what I'm going to highlight now. That is the important thing. As temperature increases, Kp values decrease for exothermic reactions. So I'm modifying the note as I go here, sorry about that. That's what you need to remember, okay? So I would probably just less focus on what's in the brackets, okay? Right, so let's have a look at the Kp value, or say Kp expression for this. So Kp, partial pressure, let's look at the equilibrium, SO3 squared over partial pressure of SO2 squared multiplied by partial pressure of O2. Okay, so remember this value here is the 500 Kelvin value. So when the temperature is raised to 700 Kelvin, the partial pressures need to change to give the new lower value of Kp, which goes down to 3 times 10 to the 4. Remember what we said at the very beginning of this, the equilibrium is achieved when we have the K value for that temperature. So the equilibrium concentrations or the partial pressures have to achieve that K value. Okay, so we've gone from 500 Kelvin, where the Kp was 2.5 times 10 to the 10. We've changed the temperature to 700 Kelvin, and the Kp's gone to 3 times 10 to the 4. So if these partial pressures don't change, they're still going to give that Kp value for 500. But that's not equilibrium because the Kp value for 700 is that. I hope I'm making sense here. So these are sort of these are how I break it down for my students. So these are the things you need to ask yourself. So has Kp got bigger or smaller at the new temperature? It's got smaller. Okay, that's straightforward, isn't it? So how do the partial pressures need to change to give the new Kp value? So if we want to make the sort of answer to the fraction lower than it was, what's got to happen? Well, the numerator term has to decrease and the denominator term has to increase. Okay, so we'll put that in. So we're making the Kp value smaller. So the partial pressures of the products need to go down and the partial pressures of the reactants need to go up. Okay, so I'll just quickly go through that very carefully again. To make this number smaller for the new temperature, that's got to go down and that's got to go up. So how does the equilibrium achieve that? It shifts left. Okay, so that's a very different way of explaining an equilibrium shift than you would in year 12 if you had to explain it just using Le Chatelier's principle. So Le Chatelier's principle, all you would need to say is the equilibrium favours the endothermic reaction, which is the reverse reaction. Whereas in year 13, it's a bit trickier. Okay. So we'll look at endothermic reactions now, and I'm going to bracket out. I'm not going to bother with this because I'm sort of looking back at it now thinking, nah, that's just going to confuse people. So there's the sign that it's endothermic. So let's have a look at what's happening here. As the temperature is increasing, so we're going from 700 to 1100 Kelvin, what's happening to Kp? It's gone from 5 times 10 to the minus 13 to 4 times 10 to the minus 8. So in other words, the Kp value increases now. And that's true for all endothermic reactions. So I'll just write that there. For endothermic reactions, as temperature increases, Kp values also increase. I'll highlight that because that is the important bit there. I'm ignoring the bracket. I'm going to delete them from the notes actually, so that's potentially confusing. Now I'm looking at it again. Right, so let's look at the Kp expression. So Kp is going to be the partial pressure of the NO squared over partial pressure of the N2 multiplied by the partial pressure of the O2. So that value there, that there is the value for 700 Kelvin. Okay. So if you increase the temperature, these partial pressures, if they don't change, will still give that value, which is the wrong value for 1100 Kelvin. So the partial pressures have got to change to get the new Kp value. So hopefully this will make a bit more sense now. It's the sort of second time you've seen it. Okay, so I've got that written there. So there's the three questions to ask yourself. Has Kp got bigger or smaller at the new temperature? It's got bigger. It's gone to 10 to the minus 8 rather than 10 to the minus 13, so it's got bigger. How do partial pressures need to change to give a bigger Kp value? So the numerator needs to increase, the denominator needs to decrease. So that's the partial pressures of the product needs to go up. The partial pressures of the reactants needs to go down. How does the equilibrium do that? To get a greater partial pressure of products than reactants than you had before, the equilibrium shifts over to the right. Okay. So you can see in red there, basically the equilibrium shifts in order to get the new value for the equilibrium constant. And then I'm not going to do Kc because it's exactly the same explanation, exactly the same. Okay, so we're moving on to explaining equilibrium shift for changes in concentration or pressure. So I'll just turn my notes over. So what have we got here? Remember that the value of an equilibrium constant, so we're talking about Kc or Kp, is unchanged by changes in concentration or pressure. So in this case, the equilibrium shifts in order to keep the equilibrium constant at the same value. Okay, so when you change in temperature, the equilibrium shifts to get the new value for K or Kc or Kp, whereas now the equilibrium shifts to get the same value as you had before. So hopefully that'll make sense when we start looking at some examples. Right, so the easiest one is the explaining the change in concentration. So suppose at temperature X, the equilibrium constant for Kc was found to be 16 moles per decimeter cubed. Okay, so Kc expression for the equilibrium above is, now we've got concentrations here, so I need square brackets, NO2 squared over N2O4. Now suppose while at the same temperature, that's key, temperature's the same, so basically we've got to keep that at 16 moles per decimeter cubed. The equilibrium concentration of N2O4 was increased from its original value. Okay, so let's imagine that's been increased. The N2O4 concentration is increased. So what would that do? A bigger denominator than you had before would lower Kc. So it's changed the Kc value, so it's no longer in equilibrium. So the equilibrium needs to get back to that value of 16 moles per decimeter cubed. So to restore Kc to its value for that temperature, the equilibrium needs to increase the NO2 concentration, decrease the N2O4 concentration. Okay, so remember that's increased, so that's changed that Kc value. Because we're at the same temperature, Kc needs to get back to that value. So how does it bring itself back up? It's going to go, that's going to go up, and that's going to go down. So how does it do that? The equilibrium shifts to the right. Everyone's very quiet today. I think we're just sort of focusing on this by the looks of it. sometimes what I say to my students is, you've got to be careful if you do this, okay, but it's a way to think about it. If you're explaining this in terms of Le Chatelier's principle, if you increase that, the equilibrium shifts that way to get back to it, to minimize the change. An increase in a reactant concentration forces an equilibrium over to the right hand side. But that's explaining it in terms of Le Chatelier's principle. If you explain it in terms of Kc, you've got to talk about how does the equilibrium keep that Kc value at, for this case, 16. Okay, so it's a slightly different way of explaining it. So we'll just flip the scenario now. Now suppose while at the same temperature, the equilibrium concentration of NO2 was increased from its original value. So NO2 was increased from its original value. So in other words, this has gone up. What's that going to do? It's going to make Kc get bigger because the numerator's got bigger. That's knocked it out of equilibrium because the Kc is at the wrong value for that temperature. So we need to bring the Kc back down. How does it do that? It lowers the NO2 concentration and increases the N2O4 concentration. So the equilibrium is going to shift backwards. So let's get that in. So this would increase Kc. So I've just got a little thing in my notes there just for clarity. Numerator has increased. That's why Kc is increased. It's not an equilibrium anymore because it's at the wrong value for that temperature. So to restore Kc to its value for that temperature, the equilibrium, what does it need to do? It needs to lower the NO2 concentration, increase N2O4 concentration. So it does that by shifting left. So you can see in red there, basically the equilibrium shifts in order to get back to the value for the equilibrium constant for that temperature. So the change in concentration actually changes the value for Kc. It's not allowed to change because the temperature hasn't changed. So how does it sort of shift to get everything back to the value for that temperature? Okay, nearly finished, which is great. Only trouble is, this is probably the worst one. Shouldn't laugh. Right, okay. Explaining the shift in an equilibrium from a change in pressure now. So we're doing this in terms of the equilibrium constant, not in terms of Le Chatelier's principle. But you could always use Le Chatelier's principle to sort of get it into your head which way the equilibrium is going to shift. Okay. So we're now going to consider why changing the pressure of the N2O4/NO2 equilibrium causes the observed shift in equilibrium position. Right, so there's the equilibrium. We already know from AS that an increase in pressure will cause the equilibrium to shift to the left because there are fewer moles on the left. So we already know that from our Le Chatelier's principle. Remember, we've got 1 mole on this side of gas, 2 moles on this side of gas. Increase in pressure favours the side with the fewest moles. Okay, so that's Le Chatelier's principle way of explaining it. We already know also from AS that a decrease in pressure will cause the equilibrium shift to the right because that side has the most moles, because there's more or most. I'll put more, it doesn't sound right, most. There's more moles on the right. Okay, so far so good, hopefully. So for the equilibrium above, the Kp expression looks like this: partial pressure of NO2 squared over the partial pressure of N2O4. Right, so what you've got to remember for this is that that's meant to represent a sealed container. So inside this sealed container, you've got NO2 and you've got N2O4, and their partial pressures both contribute to the total pressure. Okay, so if you double the pressure in that system, so if you sort of increase the pressure on this twofold, what's that going to do? It's going to double the partial pressures of all of the species in the reaction, okay? Because you've got both of those species are actually present, okay? So if you increase the pressure on the system, then all of the pressures will increase because they're all there, okay? Right, so here's the sort of tricky bit coming up now. From the Kp expression, we can see that hopefully that the numerator term, so the one on the bottom, sorry, one on the top, I always get them mixed up, the numerator term will be affected more than the denominator term. Okay, so let's just explain that. So if that partial pressure is doubled and that partial pressure is doubled, this numerator term is going to be affected more because it's being squared. Okay, so basically to explain the effect of pressure, you need to look at which side's got or has got the highest power, basically. Okay, so if these both double, this one's affected more, the top's affected more because that doubling gets squared. Okay, and that's down to a difference in the powers. So what's that going to do? That's going to cause the value of Kp to increase, because effectively this is increasing more proportionately to that one. Okay, so this increases more relative, I should say relative really, to that one. Okay, so that would cause Kp to increase because the top has got proportionately or relatively bigger than that one's got bigger. That's knocking the system out of equilibrium because we're at the wrong Kp value for that temperature. So to restore Kp, how does it shift around to get back down? Because it needs to go down in this scenario. The partial pressure of the N2O4 needs to increase. And the equilibrium does that by shifting to the left. Okay, so it's all about the powers, all about the powers. We'll just deal with this one. For the equilibrium below, we can use this concept to explain why a change in pressure of the system has no effect on the equilibrium position. So Kp for this one is the partial pressure of Hi squared over the partial pressure of H2 times the partial pressure of I2. Okay, so for example, doubling pressure of the system will double all partial pressures okay, so this partial pressure here would be times 2, this would be times 2, this would be times 2. So why would there be no effect on the equilibrium position? Because if you think about it, what have we got on the top? We've got the doubling squared, so that's fourfold, isn't it? On the bottom, we've got times 2, which is 4. So in other words, there's no change in the partial pressures, sort of, they're changing proportionately, basically. Okay, or the ratios staying the same, you could think of it like that. Okay. So what we can say there is numerator and denominator terms affected equally. So Kp stays the same. I'm going to have to write this down here, sorry. Therefore, Kp stays the same. So equilibrium doesn't need to shift. Okay. And then the final page, tiny amount of left over here, nice and easy this bit. Explain the effect of a catalyst on the equilibrium constant. Equilibrium constants Kc and Kp are unchanged by the addition of a catalyst. And remember, that's because the catalysts increase the rate of both reactions equally. So the net effect of that is the position of the equilibrium is unaffected. They just get to equilibrium faster. That's all. That's the only difference. But the position stays the same. So we've got a load of space here. So I've got a few extra little sort of things that I would tell my students, sort of key things. So change in temperature. Need to find the new Kc or Kp value. That's why it shifts, to find the new Kc or Kp value. The change in pressure or concentration. We need to get back to the original Kc or Kp value for that temperature. And then a final thing, change in pressure. Term with highest power is affected the most. Okay. Right, so what time is it? 4 minutes to 4 minutes to 4, 5 to 4. So I'm just looking at the questions. Thank you, Laura. I was a bit worried as I was talking through that I was just sort of, there's no getting away from it. I was blasting through that. I wasn't really sort of taking any questions or anything like that. If I was in class, I would be looking for students sort of looking a bit lost. Explain that. It's not I don't think that's a particularly easy concept to get your head around. So thanks for that. L. Allen, when you change the concentration / pressure, the Kc remains the same. Well, if the equilibrium doesn't shift, Kc won't be the same, because if you change the concentration, for example, of one of the components, you've knocked it out of equilibrium. So the shift is referring to what the equilibrium has to do to get the ratio back to the Kc value for that temperature. Okay, so that is what that's how I would answer your question. Okay, so the Kc, if the equilibrium doesn't change, if it doesn't shift position, then it's not an equilibrium anymore, because the Kc or Kp value is at the wrong value for that temperature. I would advise, obviously, don't just go on the way I'm explaining it. Check out other textbook explanations and things like that, and get as many different ways of explaining the same thing as you can, and then you come up with your preferred way of doing it. Okay, that's what I would say there. I've got some requests for Year 2 rate equations, so sounds like people want to do rates of reaction. I've also had a request for spectroscopy. Yeah, somebody's asked for spectroscopy. I don't know if you've noticed, but I am churning out daily videos now, exam paper walkthroughs. So I've just I recorded it this morning, so I'm going to upload an NMR question. So it's not really a teaching video, it's kind of explaining how to answer a question. If you're after teaching videos, like I always say every single week, go to my video index, and I've got the whole of NMR taught like in teaching videos where I'm actually explaining things. I think I've probably got about 6 or 7 NMR videos where I take each key point in turn, and that's a little video. And I've also got quick revision videos, which sort of blasts through the essentials, but I always advise people to watch them once you've got your head around something, because there's not much explanation in those, it's just remembering the key basics. They tend to be what I would get students to watch before the exam, so they've been taught it, hopefully they understand it, it's just a refresher really. You're welcome. Alan, I hope that made sense. Okay. All right, the water. I think you asked me that at the start, and I skipped it. Sorry, I'll go back to that for you. Kp for water and steam. Yeah, okay, got it there. Right. Yeah, so the Kp expression for the water steam, well, because Kp only involves gaseous substances, Kp would be the partial pressure of H2O. Now, because you've got steam and liquid in that, I would recommend the state symbol goes in there. So that's what that would be. So that would be that one. And the equilibrium constant Kc would just be square brackets H2O gas, because obviously liquid water is, well, pure liquids have a fixed concentration, so that would be missed out of the Kc expression. Okay, sorry about that. Okay, bang on 1600 hours. Don't know what the weather's like at your part of the world, but it's just stopped raining here in sunny Sunderland, not? So, yeah. Right, I think that's it for me, guys. So have a nice weekend. Keep an eye on. You're welcome. Keep an eye on the the channel, so have a look at the examples. Heavy rain. So where's that, Laura? If you don't mind me asking. Keep an eye on the channel. So hopefully I'm posting videos that you're welcome, Luke. You're welcome, Rebecca. Nice to see some familiar names there, my students. You'll have to let me know how much of that made sense, Luke and Rebecca. Oh, Saula. Hi, Saula. Nice to see you as well. I hope that made sense for you. So a lot of people asking for rates of reaction. Haven't decided yet. I'll put something in the what's it called, the community part of the page, and I'll make a video once I've decided. Rates of reaction mightn't be a bad shout actually. Okay. All right then. Cheers. See you later. Bye.